Imagine dropping a toddler onto a freshly waxed floor, like an incredibly slippery floor.
Oh boy. Yeah, that sounds like a disaster.
Right. And you blindfold them, spin them around, and just tell them that somewhere in this room is a piece of candy.
Okay, cruel, but I see where you're going with this.
Yeah, and every time they try to take a step, they might just slide sideways or, bump into a wall. You aren't giving them directions. No warmer or colder
Right,
hints.
zero feedback.
Exactly zero until the literal moment they stumble over the candy and you just hand it to them. It sounds like absolute chaos, right? Like a terrible way to teach someone to navigate a room.
It's basically the worst parenting strategy ever.
Totally. But mathematically speaking, this is literally the architecture we use to train an AI to conquer really complex, uncertain environments.
Yeah, it's the ultimate trial by fire. I mean, when we talk about machine learning, the default mental model most people jump to is supervised learning.
Right, where you have a teacher.
Exactly. You have this massive data set of inputs, your X variables, and perfectly labeled outputs, your Y variables. You're building a function that maps the pixels of a photo to the label cat.
Yeah, an engineer acts as this, omniscient teacher, giving the exact correct answer for every single data point.
Right, and the algorithm just calculates the error and adjusts. It's high-dimensional curve fitting, basically.
Even with unsupervised learning, where you drop the labels and just ask the algorithm to find patterns in the X data, the underlying data structure is still handed to you on a silver platter. You have the map before you take a step.
But the architecture we're diving into today completely shatters that paradigm. Reinforcement learning, or RL, just strips away the omniscient teacher entirely.
Right, you're on your own.
You are given a state, which is your current reality, and you are given a reward signal, just a sparse numerical payout. No one gives you the correct action to take.
So the algorithm has to generate its own training data.
Exactly. By interacting with the world, making mistakes, and figuring out the causality of its actions over these really long time horizons.
And if you're listening to this deep dive right now, you are likely staring down a massive engineering challenge for your final project.
Oh, absolutely.
You've got to build agents that can navigate this exact kind of chaos. Specifically, writing the Python code to solve a discrete environment, which is the casino game of Blackjack.
A classic.
Yeah, and a continuous, unforgiving physics simulation known as CartPole. And since you have a long commute ahead of you, you're probably sitting on a bus right now for an hour and a half, we're going to use this time to bridge the gap between those dense mathematical notations in lectures 16 and 17 and the actual architecture you need to build.
Yeah, we aren't going to just read you textbook definitions. We're going to completely deconstruct the mechanisms.
Practical examples only. So to build an agent that can learn from a messy world, we first have to figure out how to translate a physical world into a mathematical structure, right? Something a computer can actually hold in memory.
Right, we need a framework. And that framework is the Markov decision process, or MDP.
Let's visualize this universe before we try to solve it. Let's strip away the complexity of a physics engine for a second and just imagine a simple grid, like a 3x4 grid on the floor.
Okay, I'm picturing.
You start in the bottom left. In the top right corner, there is a green square. If you step on it, the universe hands you a reward of +1.
Nice.
But right below that green square is a red square. Step on that, and the universe hits you with a penalty of -1. And maybe there's a concrete pillar in the middle of the room you have to walk around.
That grid perfectly isolates the 4 structural pillars of an MDP. First, you have the state space, which is denoted as S.
So in software terms, that's what.
A state is the complete set of variables required to uniquely identify the agent's current reality. In your grid world, it's literally just a simple integer tuple representing your x, y coordinate.
Okay, then you have the action space. Those are the specific legal maneuvers you can execute from your current state.
Right. Up, down, left, right.
Third is the reward function. This is your scalar feedback signal. And it's really crucial to understand that the reward function isn't a strategy guide.
No, not at all. It is purely the task description. The universe doesn't give you +0.1 for taking a step toward the green square. It gives you 0 everywhere and +1 only when you finally arrive.
It's brutal. And this brings us to the fourth pillar, which is where the engineering gets notoriously difficult. The transition model, the actual physics of the world.
Right. If the universe is deterministic, programming an agent is trivial. If I'm in state 1, 1, and I execute the action up, I will arrive at state 1, 2 with absolute certainty.
The probability is basically 1.0.
Exactly. I can just calculate a static path of the green square. Up, up, right, right, right. Done.
But physical reality and the environments you have to build for your project are stochastic. They contain inherent randomness.
Yeah, let's bring back that slippery floor scenario from the lectures. You command your agent to go up. But because the floor is slick, that action only executes exactly as intended, say 80% of the time.
So there's an 80% chance I actually move to the square above me.
Correct. But there's a 20% chance the agent just loses its footing. Let's say it slips at a right angle to its intended path. A 10% chance it slides left, and a 10% chance it slides right.
Which immediately destroys any concept of a pre-planned script. I mean, I can't just queue up a list of strings like up, up, right, and run a for loop.
Nope, that won't work at all.
Because on step 1, I try to go up, that 10% probability hits, and I slide left into a wall. My entire script is now invalid because I'm not in the state the script expects me to be in.
This means our transition model isn't a simple mapping. It's a three-dimensional probability tensor. It's a function, t of s, a, s prime, that takes your current state, your chosen action, and a potential next state, and returns the probability of that specific transition actually occurring.
Now, I have to challenge an assumption here, because this trips up a lot of people. If the floor is slick and my agent keeps sliding into the left wall, shouldn't it build up a memory of that?
You would think so, right?
Yeah. Shouldn't it realize, hey, every time I'm in this specific quadrant, I slip. I should remember my past trajectories to inform my next move. Why does the math explicitly forbid the agent from using its past?
You're touching on the fundamental bottleneck of computation. We enforce what is known as the Markovian property. The formal definition states that the probability of transitioning to the next state depends only on the current state and the current action.
It's completely independent of the history.
Entirely independent. The universe has no memory. It doesn't care how you got to the square you were standing on.
Well, why?
Think about the memory complexity if we didn't enforce this.
Yeah.
If your decision at step 50 required evaluating the specific sequence of the previous 49 steps, the number of possible unique histories in even a tiny 3x4 grid would just explode into the trillions.
Oh, wow. Yeah.
You could never store that matrix in RAM, let alone compute gradients on it. By assuming the Markov property, we compress the entire causal history of the universe into the current state variable.
That is a massive architectural constraint, though. It means when you design your state space, you have to ensure that every single piece of data necessary to make an optimal decision is encoded right there in the present moment.
Exactly.
Let's map this directly to the first challenge in the listener's engineering pipeline, Blackjack V1.
Oh, Blackjack is a masterful demonstration of a discrete stochastic MDP. But you really have to define the state space carefully.
Right, because the state isn't the entire sequence of cards dealt from the shoe.
No, not at all. If you've been dealt a 2, a 4, and a 10, giving you a total of 16, the agent doesn't need an array storing 2, 4, 10. By the rules of the game, the only variable that dictates your probability of busting on the next hit is the sum itself, 16.
So the state representation shrinks dramatically. The agent needs its current sum, which realistically ranges from 12 to 21 because, I mean, anything under 12 you would automatically hit.
Right, it's a forced move.
It needs the dealer's visible up card, which is a value from 1 to 10. And it needs one more crucial piece, right? The usable ace.
Yes, the usable ace is huge. An ace can be a 1 or an 11.
Yeah.
If you have an ace and a 6, your sum is 17. But if you hit and draw a 10, you don't bust at 27.
The ace degrades to a 1.
Exactly. And your new sum is 17 again. The presence of a usable ace fundamentally alters the transition physics of your next action.
So our complete state space is actually incredibly compact. You have player's sum, which is 10 possibilities times dealer card, another 10 possibilities, times usable ace, which is just 2 possibilities.
200. That's a matrix of exactly 200 discrete states.
That's nothing. We can easily hold a 200-row table in memory.
Easily. And the transition model, the stochastic physics we were talking about, is handled natively by the deck of cards. When you choose the action hit, the environment calculates the probability of drawing a 2, a vase card, or an ace, and transitions you to a new player sum. You don't know which state you'll land in, but the probability distribution is mathematically fixed.
Okay, so we've built the arena, we have 200 states, we have our actions hit or stick, and we know the transitions are driven by probability. How does the agent actually architect a winning strategy?
Well, the output of our algorithm isn't a static plan. It's a policy. denoted by the Greek letter pi. A policy is basically a universal reflex manual.
Like a lookup table.
Exactly. It's a dictionary where the keys are every single possible state in the universe, and the values are the optimal action to take in that specific state.
It's an interrupt-driven architecture. Like, if you wake up in state 42, execute action A. If you wake up in state 105, execute action B. The agent doesn't care how it got there. It just looks up its current reality in the dictionary and fires the corresponding action.
But populating that dictionary is where we run into the credit assignment problem.
This is a big one.
Yeah. Let's look at the reward structure of Blackjack. You don't get points for drawing a 7. You get +1 for winning the hand, -1 for losing, and 0 for a draw. And you only receive that reward at the very end of the sequence, the terminal state.
So if I choose to hit on 14 and then hit on 16 and then stick on 20 and I win, which action gets the credit?
Right. Was hitting on 16 a genius move, or was it a mathematically terrible decision that just happened to get bailed out by a lucky 4?
The agent has to propagate that delayed terminal reward backward through time. It needs to calculate not just the immediate reward of a state, but the expected long-term accumulation of future rewards. We call this true underlying value, the utility of a state.
And here we had another massive mathematical roadblock. If we just sum up infinite sequences of future rewards, our expected values will blow up to infinity.
Yeah, an agent stuck in a loop just gathering +1 rewards forever would have a utility of infinity. You can't write a Python script to optimize for infinity.
No, your computer will not like that. This introduces one of the most critical hyperparameters you will tune for your project, the discount factor, gamma.
Gamma is fascinating because it fundamentally shapes the psychology of the agent, in a way. It's a float value between 0 and 1, usually set really high, like 0.95 or 0.99.
Gamma dictates how much the agent cares about the future. An immediate reward is realized at 100% of its value. But a reward, one time step in the future, is multiplied by gamma.
So if gamma is 0.9, a +1 reward tomorrow is only worth 0.9 today.
Exactly. And a reward 2 steps out is multiplied by gamma squared, so it's worth 0.81.
It essentially acts as an exponential decay function on the future.
Right. The mathematical necessity is that it bounds our infinite sums, so they actually converge to a finite number we can store in an array.
Yeah.
But behaviorally, it forces efficiency. If the agent knows a +1 reward is sitting 5 squares away, gamma ensures the agent takes the shortest possible path. Every step it wastes wandering around, the value of that eventual reward gets multiplied by another fraction and shrinks.
Now, I often hear developers debate whether gamma is a property of the environment or a property of the agent. Like, is it physics or is it strategy?
That's a great question. The architectural consensus is that the states and transition probabilities are the objective physics of the world. But the reward function and the discount factor represent the task description.
They are the knobs we turn to dictate what we want the agent to prioritize.
Precisely. If you set gamma to 0.1, the decay is so aggressive that the agent becomes incredibly short-sighted. It will grab any immediate penny and completely ignore $1 million just 3 steps away.
But if you set it to 0.999, the agent becomes a strategic mastermind, willing to endure hundreds of steps of zero reward for a massive payoff.
So we have a mechanism to decay future rewards. But how do we actually calculate the utility of all 200 Blackjack states? We use the foundational algorithm of dynamic programming, the Bellman equation.
The Bellman equation can look pretty impenetrable when written out with all those sums and max operators on the slide, but its logic is brutally elegant. It relies on recursion.
Yes, it states that the true utility of any given state is equal to the immediate reward you get for being there, plus the discounted expected utility of the best possible state you can reach next.
Wait, let's slow down and unpack the expected part of that, because that's where the transition matrix actually lives in the code.
Good point. Let's go back to the slippery floor. You're in a state, and you evaluate the action up. Because of the 80-20 stochasticity, you don't actually know where up will take you.
Right.
So, the Bellman equation iterates through all the possible states you might land in. It takes the utility of the state above you and multiplies it by 0.8. It takes the utility of the state to your left and multiplies it by 0.1. It takes the utility of the right state and multiplies by 0.1.
And then it just sums those up.
Exactly.
Yeah.
That is the expected utility of taking the up action.
And then it calculates the expected utility for down, left, and right. And the max operator simply grabs the highest resulting float value from those 4 calculations.
You've just described a single step of value iteration.
Let's explicitly trace how a developer writes a value iteration loop in Python, because it is strictly required for the project. You start with an array representing your utilities, v. You don't know the true values yet, so you just initialize the entire array with zeros.
Right. Obviously, an array of all zeros is a terrible policy.
Yeah.
But then you execute a sweep. You loop over every single state in your state space. For state 0, you look at its neighbors, calculate the expected value for each action using the Bellman equation, find the maximum, and overwrite the 0 in v0 with this new, slightly better estimate.
But wait, if I'm evaluating state 1,1 and I look at the state above it to pull its utility, that neighbor's utility is also currently 0. If I multiply 0 by a transition probability, I just get 0. Seems like the math would just sit there returning zeros forever.
Ah, this is the magic of the terminal states. Your loop will eventually hit the squares adjacent to the green reward square. The green square has an immediate inherent reward of +1.
Okay, I see.
So when a state right next to it evaluates its right action, it pulls in that +1. That specific state's utility updates from 0 to, say, 0.9.
Oh, wow. So on the first sweep across the matrix, only the states immediately bordering the goal light up with a non-zero value.
Precisely. And then you sweep again. On the second sweep, the states that are 2 steps away from the goal will look at their neighbors, see the 0.9 value that was just established, apply the Bellman equation, discount it, and update their own value to 0.81.
It's like a wave of informational gradient slowly propagating backward from the goal, washing over the entire state matrix, sweep by sweep.
That's a great way to visualize it. You
Yeah.
just run that while loop, sweeping the entire state space over and over.
But that raises a critical engineering question. When does the while loop actually break? Like, when do we stop sweeping? The specifications require a strict convergence criterion.
In your code, you need to track the magnitude of the updates. During a sweep, you calculate the new utility for a state. You subtract the old utility from the new utility and take the absolute value. This is the delta for that state.
Okay.
You keep track of the maximum delta across the entire sweep. We call this the L-infinity norm.
So if state 42 changed its value by 0.5 and state 18 changed by 0.1, the max delta for that sweep is 0.5.
Right. And you set a hyperparameter, a tiny threshold like 1 e minus 5. Once your maximum delta across an entire sweep drops below that threshold, it means the wave of information has settled.
The values are no longer fluctuating.
Exactly. The array has converged on the true, mathematically perfect utilities. You break the loop.
And once you have that perfect V-array, extracting the policy is literally a one-liner. For any state, you just run the Bellman calculation one last time and argmax it. You pick the action that yields the highest expected value. You now have an optimal agent.
Now, the project also requires you to implement policy iteration. The architecture here is slightly different. Instead of refining a value array until it's perfect, policy iteration starts by initializing a completely random policy dictionary, like always hit no matter what.
Which is a terrible strategy.
A completely terrible strategy. But the algorithm then enters an evaluation phase. It solves the linear system to figure out exactly how terrible that policy is. It calculates the values, assuming the agent is strictly forced to follow that random rulebook.
So it's not taking the max over actions anymore. It's just evaluating the singular action dictated by the current flawed policy.
Right. And once it computes those values, it enters an improvement phase. It iterates through the states and asks, if I deviate from my current policy for just one step and pick a different action based on these new values, would my expected return go up?
And if the answer is yes, it updates the policy dictionary.
Yes. It bounces back and forth, evaluate the policy, improve the policy, evaluate, improve. Both value iteration and policy iteration will mathematically guarantee finding the optimal policy.
Okay, take a breath. What we just described, dynamic programming, looping over transition matrices, is incredibly powerful, but it fundamentally relies on one massive assumption.
That you possess the transition matrix.
Exactly. You have to know the exact probability of slipping on the floor. You have to know the exact probability of drawing a 10 from the shoe. We call this model-based planning.
But what happens when you don't have the model? What happens when you are dropped into an environment where the physics are completely hidden, the probabilities are unknown, and the reward function is basically a black box?
This is the true frontier. This is reinforcement learning proper. Sectioning off from planning, we move into learning from raw, chaotic experience.
You no longer have a while loop iterating over an abstract state space in memory. You have an agent actually interacting with an environment in real time. The agent finds itself in state S. It chooses an action A. The black box of the environment processes that action and spits back a new state S prime and a reward R.
A transition tuple, SARS prime.
That tuple is the fundamental atom of reinforcement learning. It is a single unit of empirical experience. And the algorithms you have to build, SARSA and Q-learning, use these isolated tuples to estimate the true utilities without ever attempting to reverse engineer the underlying transition matrix. This is called temporal difference learning, or TD learning.
The major architectural shift here is that we stop calculating the value of a state. Instead, we calculate the value of a state-action pair. We call these Q values.
Right. A V value says being in state 16 is worth 0.5. A Q value says being in state 16 and taking the action hit is worth 0.7.
This distinction is critical because if you don't know the transition probabilities, having the V value doesn't help you pick an action.
Right. You can't look ahead to see what action leads to the best state if you don't know where the actions actually go. By storing the values of the actions directly, you just look at your Q table for state 16, see that hit is 0.7 and stick is 0.2, and you pick hit.
So we initialize a massive Q table with zeros. How do we update it using just that single tuple of experience?
Let's look at the update equation. It is the heartbeat of both SARSA and Q learning. You take your old Q value estimate, then you calculate a target based on your new experience. That's immediate reward R, plus the discounted Q value of the next state, S prime. You compare this new target to your old estimate to get the temporal difference error.
If the target is higher than my old estimate, the error is positive. I was too pessimistic.
Exactly.
Yeah.
You multiply that error by a learning rate, denoted by alpha, and you add it to your old estimate.
Alpha is fascinating. It acts as an exponential moving average. If alpha is 0.1, you are basically saying, I'm only going to update my Q value by 10% of the error. I'm not going to completely overwrite my belief based on one single noisy transition.
It smooths out the stochasticity of the environment over thousands of episodes.
Now, your core assignment is to implement and explicitly compare SARSA and Q learning, and the difference between them hinges on a single, incredibly subtle philosophical choice regarding how they calculate the value of the next state, S prime, when constructing that target.
Let's break this down meticulously. SARSA stands for state, action, reward, next state, next action.
So SARSA is an on-policy algorithm. It is brutally realistic.
Yeah, when SARSA lands in state S prime, it has to estimate the value of S prime to update its previous move. To do this, SARSA actually queries its current policy to see what action it is planning to take next. Let's call it A prime. SARSA uses the Q value of that specific intended action to update its table.
So if SARSA's current behavioral policy includes a 10% chance of doing something completely random, and the policy decides that its next action is going to be a terrible random move that drives it off a cliff, SARSA incorporates the negative value of that terrible move into its current update.
Right. It says, look, I know there's a mathematically perfect path over there, but knowing my current sloppy behavior, I'm probably going to mess up, so I better lower my value estimate right now.
SARSA evaluates the policy it is actively executing, flaws and all. Q-learning, on the other hand, is an off-policy algorithm. It is an incurable optimist.
Totally wildly optimistic.
How does the Q-learning target differ mathematically?
When Q-learning lands in state S prime, it completely ignores its actual behavioral policy. It doesn't care what action it's about to take. It sweeps across all possible actions available in S prime in its Q table, and it simply grabs the absolute maximum value.
It just assumes, from this moment forward, I'm going to execute the mathematically perfect sequence of actions, even if its current code is forcing it to act randomly to explore.
Let's visualize the behavioral difference with the classic cliff walking problem. Imagine a grid world where the shortest path to the massive plus 100 reward runs right along the edge of a cliff. If you step onto the cliff tiles, you get a catastrophic minus 1,000 reward and you reset.
Okay, I see where this is going. Because Q-learning updates its targets based on the max action, it assumes it will never accidentally step off the cliff.
Exactly. It learns a Q table that says the optimal path is a razor's edge sprint right next to the abyss. The theoretical values converge on that risky optimal path.
But wait, during training, the agent isn't acting perfectly. It's exploring. It's taking random steps to learn the environment. So if Q-learning is following a policy that says walk along the edge, but the exploration logic occasionally injects a random sideways step, Q-learning is going to repeatedly hurl itself off the cliff during training.
Yeah, it's going to rack up massive negative returns. You're touching on the fundamental flaw there. Q-learning learns the optimal policy, But its execution of that policy during training can be catastrophic if exploration is high.
Now look at Sarsa.
Right. SARSA incorporates its exploration randomness into its updates. When it evaluates the tiles next to the cliff, it factors in the reality that I have a 10% chance of taking a random step, and a random step here equals death.
So the Q values for the tiles near the cliff become highly negative.
Exactly. SARSA learns a safer, more conservative path, routing the agent far away from the edge. Its theoretical maximum return might be slightly lower because the path is longer, but during training, it actually survives.
This is exactly what you need to document in your final report. You must run both algorithms under identical exploration parameters and graph their learning stability. Q-learning's curve might look chaotic and noisy because of its off-policy optimism crashing into reality.
While SARSA might show a smoother, more stable convergence because it adapts its policy to account for its own clumsiness.
And that leads us directly into the architectural mechanism that dictates that clumsiness. The exploration-exploitation dilemma.
You are dropped into a completely unknown matrix. All your Q values are 0. How do you actually decide which action to take to generate those transition tuples?
The standard heuristic is the epsilon greedy strategy. Let's explain this not with the standard restaurant analogy, but by looking at the actual code logic.
Sure. You define a hyperparameter epsilon as a float between 0.0 and 1.0. Inside your agent's choose action function, the first thing you do is called numpy.random.random. You generate a random float between 0 and 1.
You set up a simple conditional statement. If that random float is greater than epsilon, you exploit. You query your Q table for the current state, run an argmax, and execute the action with the highest known value. You trust your historical data.
But if the random float is less than epsilon, you completely bypass the Q table. You call a function that returns a completely random integer from your action space. You explore.
Typically, you start training with epsilon at 1.0, 100% exploration. Your Q table is empty, so trusting it is useless anyway.
The agent flails wildly, executing a random walk through the environment, bouncing off walls, accidentally stumbling into rewards, and slowly populating the Q values via TD updates.
Then, you implement an exponential decay schedule. After every episode, you multiply epsilon by a decay rate, say 0.995. Over thousands of episodes, epsilon smoothly shrinks. 1.0, 0.9, 0.5, 0.1.
The agent gradually shifts from chaotic exploration to precision exploitation of the optimized paths it has discovered.
The architectural trap here is letting epsilon decay to absolute 0. The project guidelines explicitly warn against this. Why is a 0 epsilon mathematically dangerous?
If epsilon hits 0 at episode 500, but your training runs for 5,000 episodes, your agent is entirely locked into its current beliefs. If it found a suboptimal, mediocre path early on, it will exploit that path forever.
It has disabled the mechanism required to discover that a better path exists just 2 squares over.
Right. You suffer from premature convergence.
So you have to code in an epsilon floor. Epsilon equals max of min epsilon, or epsilon times decay rate. You set that floor to, say, 0.01. So even at episode 10,000, when the agent is a master, 1% of the time it still tests a random action just to verify its assumptions.
There is an alternative to epsilon greedy that relies purely on math rather than a random number generator. It's incredibly elegant for tabular environments. It's called optimistic initialization.
Let's take that a step further. We talked about initializing the Q table with zeros. What if we initialize it with a massive, mathematically impossible number?
Let's say the maximum possible cumulative reward in an environment is plus 10. You initialize every single float in your Q table to plus 100.
You instantiate an agent that is functionally delusional.
Yes, but watch the behavior it generates. Epsilon is set to 0. Pure greedy exploitation. The agent wakes up in state S. It looks at its actions. Up is worth 100. Down is worth 100. Left is 100.
It picks up because they are all tied for maximum.
It executes the transition, gets a normal reward of, say, 0, and runs the TD update.
It calculates the error. The target is 0. The old estimate was 100. The error is massive and negative. It multiplies by the learning rate, and the Q value for up drops from 100 down to, say, 90.
On the very next step, the agent is back in state S. It looks at the table. Up is now 90. But down, left, and right are still 100, so it greedily chooses down.
It naturally explores every single action without relying on a random if statement. The mathematical optimism forces it to exhaustively test the entire state action space, systematically grinding down the artificially inflated values until they match reality.
The exploration is driven by the gradient of disappointment.
It's a phenomenal trick, but it only works seamlessly in tabular environments, which brings us to the hardest pivot in your engineering assignment, CartPole V1.
Yeah, so far, our Q table has been a simple Python dictionary or a small NumPy matrix. Blackjack had 200 discrete states. A grid has 12. We just index into a row and grab a value. But CartPole breaks this paradigm entirely.
CartPole is a continuous physics simulation. The environment state is a vector of 4 floating point variables. You have the cart's position on the track, the cart's velocity, the angle of the pole attached to the cart, and the angular velocity of the pole's swing.
The pole angle isn't leaning left or leaning right. It's a float, like 0.1245 radians or 0.1245001 radians.
The state space is mathematically infinite. You cannot initialize a NumPy array with infinite rows. This is the curse of dimensionality.
If you attempt to feed those raw floats into a tabular Sarsa algorithm, the agent will never visit the exact same state twice. Every single update will map to a completely unique row that will never be queried again. No learning occurs.
To fix this, we have to perform state discretization. We have to map an infinite continuum into a finite number of discrete bins.
You're taking a grid and aggressively overlaying it onto the physics engine. In Python, you typically use numpy.digitize. You define an array of thresholds. If the angle float falls between 0.0 and 0.1, digitize returns the integer bin 0. If it's between 0.1 and 0.2, it returns bin 1.
You forcefully compress the infinite variance into a discrete integer you can use as an array index.
But the architecture of those bins is where projects either succeed or melt down. Let's look at the combinatorial math. If you divide each of the 4 variables into 10 evenly spaced bins, your state space size is 10 times 10 times 10 times 10. That's 10,000 states.
Multiply by 2 actions. Your Q table is an array of 20,000 floats. That's trivial. Your laptop computes that instantly.
But what if you try to get high resolution? What if you use 100 bins per variable? 100 to the 4th power is 100 million states. Your Q table just exploded to 200 million floats.
Oh, wow.
And more importantly, your agent now has to explore 100 million states to learn a policy. Your 5,000 episodes won't even scratch the surface of that matrix.
So we have to be incredibly stingy with our bins. But if we make them too coarse, we trigger something catastrophic called state aliasing.
State aliasing is when you force 2 fundamentally different physical realities into the exact same bin. Let's say you allocate only 3 wide bins for the pole angle: leaning left, center, and leaning right.
So center covers everything from perfectly vertical at 0 degrees all the way to a 10-degree lean.
Look at the physics of that. At 1 degree, the pole is stable. You can take a gentle action. At 10 degrees, the pole has massive momentum and is about to crash. You need to take an aggressive action.
But because both realities are clamped into bin center, the algorithm evaluates them as the exact same row in the Q table.
The agent experiences massive cognitive dissonance. It looks at the center row, chooses left, and sometimes it successfully stabilizes the pole, and other times the pole instantly crashes. From the algorithm's perspective, the transition matrix appears impossibly noisy and unpredictable.
It isn't a learning failure, it's a sensory deprivation failure.
This is why you must allocate your bin density asymmetrically. The cart's position on the track barely matters for balancing the pole as long as you don't hit the edges. You can allocate maybe 3 bins to position. But the pole angle and angular velocity are highly sensitive parameters. You need 6 to 12 tightly packed bins around the center point for the angle.
You also need to utilize clamping. The physics engine technically allows the pole to spin at 5 radians per second. But practically, if the pole is spinning that fast, it's already unrecoverable. The episode is functionally over. You shouldn't waste precious bins modeling the aerodynamics of a falling pole. You just establish a threshold at, say, 3.5 radians. Anything above that gets clamped into a single terminal too fast bin.
The assignment requires you to ablate these discretization grids. You have to write code that loops through different bin configurations, coarse versus fine, and plot the impact on learning stability and wall clock execution time.
And there is a brilliant workflow hack mentioned in the parameters. Value iteration is required for CartPole, but value iteration requires a transition probability matrix. How do you get the transition matrix of a continuous physics engine? The math is a nightmare.
You don't do the math.
Mm.
You let the model-free algorithms approximate it for you. You spin up your epsilon-greedy Sarsa agent. You let it randomly thrash around the discretized CartPole environment for 10,000 episodes.
Okay.
And every time it executes a transition from bin A, using action left, to bin B, you simply log that tuple in a massive counter matrix.
You just count the occurrences. I was in bin 42, went left, and landed in bin 43 exactly 800 times out of 1,000 attempts. You divide the raw counts to get the empirical probability. 0.8.
You passively map the stochastic physics of your discretization grid simply by observing the random walk. Once you have that empirical transition matrix, you freeze it, plug it into your value iteration while loop, and mathematically solve the grid. It's a gorgeous engineering pipeline.
Which brings us to the final hurdle, the hyperparameter search. You have learning rates, gamma, epsilon decay schedules, bin architectures. If you run a naive grid search testing every possible combination of every variable, your laptop will run out of compute time before the deadline.
A nested for loop testing 5 values for 5 variables is 5 to the 5th power, which is 3,125 training runs. If each run takes 2 minutes, that's 4 solid days of computation. You cannot brute force this.
You must implement a successive halving strategy. This is essentially a survival of the fittest algorithm for hyperparameters. Explain the statistical justification for why we can cut corners here.
In tabular TD learning, early random exploration establishes the baseline gradients of the Q table. If a specific combination of learning rate and epsilon is functionally broken, it will demonstrate that failure almost immediately.
Right.
If an agent hasn't found a single positive learning signal after 200 episodes, the mathematical probability of that specific Q table suddenly catching a useful gradient at episode 3000 is statistically near zero.
So stage 1, you randomly sample 24 different hyperparameter configurations. But you don't run them for 5,000 episodes. You give them a tiny compute budget, a 200-episode sprint.
You analyze the interim returns. The configurations that are flatlining at a score of 10, meaning the pole falls over instantly every time, are pruned. You ruthlessly terminate the bottom 50%. You're cutting dead branches from the search tree.
Stage 2, you take the 12 survivors and double their compute budget. Run them to 1,000 episodes. See which ones actually have the capacity for long-term convergence, not just early lucky spikes. Prune the bottom 50% again.
You keep iterating this process, giving more and more compute to a smaller and smaller pool of elite candidates, until you have a single champion configuration. You then do localized tweaks around that champion, nudging the learning rate up or down slightly to squeeze out the final performance. It reduces your search time by an order of magnitude.
But there is a massive caveat to measuring performance. The project explicitly requires you to run 5 independent random seeds for every model. Why? If my code works perfectly once, shouldn't that be proof enough?
Reinforcement learning algorithms suffer from extreme variance. Because your epsilon-greedy exploration relies on numpy.random, the sequence of early states your agent visits is entirely determined by the random seed.
If the random number generator happens to spit out a sequence that perfectly walks the agent to the goal on episode 1, the Q table updates perfectly, and the agent converges in 10 minutes. It looks like a genius algorithm.
But if you change the seed, the agent might get stuck in a corner for 2,000 episodes, constantly updating negative values and destroying its Q table. The exact same hyperparameter configuration can yield a beautiful learning curve or a catastrophic failure purely based on the initial dice rolls.
So a single run is a statistically invalid sample size. You have to run your champion configuration 5 separate times, initializing a different random seed each time. You average the learning curves together, and you plot a shaded variance band, like an interquartile range or a standard deviation around the mean.
The graders aren't looking for a single lucky run that hits a perfect score. They're looking for architectural robustness. A configuration with a slightly lower peak score but a tight, stable variance band is vastly superior to a volatile configuration that wildly oscillates between 0 and 500.
Now, for the ambitious engineers listening on the bus, we need to dive deep into the extra credit, the rainbow DQN ablation. This bridges everything we've talked about, tabular Q-learning and discretization, into the realm of modern deep RL.
Let's explicitly define why DQN is necessary. We spent all that time trying to carefully chop CartPole's continuous physics into discrete bins to force it into a matrix. A deep Q network removes the bins entirely.
It throws away the NumPy array. Instead of a table where rows are states and columns are actions, you build a neural network. The input layer takes the raw, continuous floating point values of the four CartPole variables.
The network passes those floats through hidden layers of weights and biases, and the output layer spits out the Q value for each possible action.
The neural network acts as a universal function approximator. It learns the smooth, continuous gradients of the state space. It realizes that a state with an angle of 0.13 are mathematically similar, so updating the weights for one naturally generalizes and updates the values for the other.
You destroy the curse of dimensionality.
But vanilla DQN has a massive, mathematically proven flaw, and the extra credit asks you to implement a component from the rainbow paper to fix it. Let's talk about double DQN because it addresses the exact same off-policy optimism problem we discussed with tabular Q-learning.
We established that Q-learning calculates its target by taking the max over the next state's actions. But when you are using a neural network to estimate those values, the network outputs contain noise. They aren't perfect representations of the true utility. They are approximations with variance.
Actually, the math implies something even harsher. If you have a set of variables with random noise, and you continually apply a max operator to them, you will systematically select the values with positive noise.
Exactly. If the true value of all actions in state S prime is 10, but the neural network's noise causes it to estimate action A as 9 and action B as 11, the max operator blindly grabs the 11. The target gets artificially inflated.
And because Q-learning bootstraps, meaning it updates its current estimates based on its future estimates, that positive noise cascades backward through the network. The Q values experience runaway inflation. The network becomes hopelessly biased and unstable.
Double DQN solves this by decoupling action selection from action evaluation. In vanilla DQN, you use the same network to find the best action and to evaluate its worth. In double DQN, you maintain two separate neural networks: the primary network, which is constantly updating, and a target network, which is a delayed, frozen copy of the primary network.
Wait, so the primary network picks the action, but the target network prices it?
Yes, exactly. When you calculate the target, the primary network looks at state S prime and says, based on my current weights, action B is the argmax. It's the best. But it doesn't supply the value. It hands action B over to the frozen target network.
And the target network evaluates action B and says, you might think it's an 11, but my older, more stable weights evaluate it as a 9.5.
You use the 9.5 as the target. By separating the argmax selection from the value estimation, you mathematically sever the positive bias loop. The overestimation drops dramatically, and the learning curve stabilizes.
Another option for the extra credit is dueling networks. This is a brilliant architectural rewrite of the final layers of the neural network.
In a standard DQN, the fully connected layers process the state and immediately output the Q values for the actions. Dueling architecture splits the final layer into two separate streams.
One stream calculates the pure value of the state, V of S. Independent of any action, how good is it just to be here? The other stream calculates the advantage of each action, A of A. Compared to the baseline value of this state, how much better or worse is choosing left versus right?
At the very end, it aggregates the two streams back together. Q of S, A equals V of S plus A of A.
But why go through the computational overhead of splitting and merging?
Think about the CartPole state, where the pole is perfectly vertical and stationary. Regardless of whether you nudge the cart left or right, the state is phenomenal. The value is incredibly high. By having a dedicated stream to learn that the state itself is valuable, the network doesn't have to waste gradient updates trying to learn identical high Q values for both the left and right actions independently.
It learns the baseline value once, and then only has to learn the tiny marginal differences in the advantage stream.
It accelerates convergence significantly in environments with lots of redundant actions.
If you tackle the rainbow ablation, your report needs to explain these underlying mechanics. Don't just paste PyTorch code. Explain why splitting the network layers mathematically outperforms the baseline tabular methods. But, as the specifications warn, time box this. Do not spend 20 hours debugging a PyTorch tensor shape error if your core SARSA code is still failing to converge on Blackjack. The tabular foundations are the priority.
We have covered an immense architectural landscape. If you've been following along on your commute, you now have the conceptual blueprints to translate lectures 16 and 17 into functioning Python code.
We started by defining the rigid matrices of Markov decision processes. We solved the recursive loops of the Bellman equation to find the mathematical ceiling of value iteration.
We stripped away the transition models to enter the realm of model-free reinforcement learning, debating the conservative on-policy updates of SARSA against the volatile, off-policy optimism of Q-learning.
We wrote the epsilon greedy logic to balance chaotic exploration with calculated exploitation and bypassed infinite continuous states using numpy.digitize and state clamping.
And we optimized the entire pipeline using successive halving to prune bad hyperparameter combinations, ensuring statistical rigor with multi-seed variance tracking.
It is a phenomenal toolkit for building adaptive intelligence. But I want to leave you with a final thought experiment as you wrap up this commute. We spend so much time tuning these hyperparameters to shape the behavior of arrays and matrices. We tweak gamma, the discount factor, to force an agent to delay gratification and seek long-term rewards. We tune epsilon to force the agent to stop exploiting its comfortable routines and explore the unknown.
The parallels to biological algorithms are impossible to ignore. After all, TD learning was heavily inspired by the dopamine reward prediction error found in mammalian brains.
Right. It forces you to look at your own behavior through the lens of an optimization function.
Yeah.
When you decide to impulsively buy an expensive coffee instead of putting that money into a retirement account, is that a character flaw, or is your biological gamma factor just tuned too low, heavily discounting a reward that is 30 years in the future?
Or, when you go to the same reliable restaurant for the 50th time instead of trying the new place down the street, have you let your internal epsilon decay to zero? Have you prematurely converged on a local optimum, completely unaware of a better state action pair just out of sight?
If we're just complex neural networks minimizing temporal difference errors based on a sparse biological reward function, what exactly is the reward we are trying to optimize? As you step off the bus, open up your code editor, and start initializing your matrices, ask yourself, what does your own internal Q table look like? Good luck on the project.